All right, so moving on to section 11.4. This section is primarily about evaluating limits at infinity. Infinity is always a abstract concept, right? Because it's not an actual number. Infinity just means as something gets really, really, really big. And also minus infinity, of course, means something gets really, 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 really small. Okay, but it's not an actual number because it keeps moving, I guess. All right, so let's go over some rational functions that you're familiar with. Right here, I have 1 over x minus 1. And of course, to find the vertical asymptote, right, you set the denominator equal to 0, x is equal to 1. And I have another another rational function that we will analyze after this one. Okay, so if I ask you, what is the limit as x approaches infinity, right? It kind of looks like a sideways 8 of this function, right? And note that there's a positive infinity and a negative infinity here. So if I'm going along the x-axis, which is right here, and I go all the way to positive infinity, right? If I extend this graph forever to the right, it looks like this curve, right? Where does my y value approach? Well, it looks like my y values are going to approach 0. And likewise, if I ask you, hey, what is the limit as x approaches negative infinity, going this direction? Notice the function is also going to approach, the curve, right? It's going to approach 0. Okay, so that answers this question, right? The limit as x approaches infinity, the limit as x approaches negative infinity, it's going to approach 0 and 0. Now, what about this graph right here? Again, the vertical asymptote is x is equal to negative 1. And here, of course, remember, I have a horizontal asymptote as well. Okay, so if I ask you what is the limit as x approaches infinity, well, as x approaches infinity to the right, it looks like the curve, right, is going to go to 2. What about the limit as x approaches minus infinity? Well, going minus infinity, going this direction, looks like the curve is also going to approach 2. Now, as you study these two graphs, right, what do these two numbers correspond to? And if you think about it here for a minute, and you said, well, those two numbers actually correspond to the horizontal asymptote, then you are correct, right? This curve where it's approaching positive infinity and minus infinity, this is just y is equal to 2, right? And this guy right here is just the horizontal asymptote. Remember in studying rational functions for the first time, if these degrees are the same, right, it's the ratio of the leading coefficients to HA is just 2 over 1. And likewise, what about this one, right? Well, these two numbers right here also correspond to the horizontal asymptote. Remember, the HA in this problem right here is just y is equal to 0. And remember when you study it for the first time, right? If this degree in the denominator is greater than the degree in the numerator, which it is, the horizontal asymptote is just y is equal to 0. All right, so now you can make that connection, right? All that stuff that you were taught to memorize back in algebra 2 or math 3, right now you are making a calculus connection where basically, key concept number 1, taking limits at infinity of a rational function corresponds to finding the horizontal asymptote. Okay? And that really is the connection. This is always going to be true when you take the limits of infinity of a rational function. Remember, a rational function has variables in the denominator. Okay? And it doesn't matter if I go to positive infinity or negative infinity. It's always going to approach the HA. Okay, now how do I do these problems algebraically without having to graph it, right? Remember, graphing rational functions is kind of a pain because it just takes a little bit of time, right? So to do it algebraically, you want to evaluate limits at infinity, and you want to evaluate limits at infinity. You simply divide by the highest power in the denominator, assuming that there's variables in the top and bottom. In numerator and denominator. Okay, so that's just a strategy that you can use to find, evaluate limits at infinity. And you're also using your limit properties that were introduced in section 11.1. Okay, so refer to that textbook page that I showed you in other videos. Okay. All right, so doing these problems are not that bad. In fact, you can probably figure out the answer without even showing it algebraically. But as I mentioned, you should always show your work on your homework, and it's good practice, for next year. Okay, so let's start with this first example. Find the limit if it exists. The limit as x approaches infinity, 5 plus 2 over x squared. What I can do on this problem right here is use my limit properties. The limit of a sum is the sum of the limits. So the limit of a sum is the sum of the limits. Basically just means I'm going to split this up. The limit as x approaches infinity of positive 5 plus the limit as x approaches infinity of 2 over x squared. Okay, now what is the limit of a constant? Right, this is just, think of this as a function, y is equal to 5, right? This is a horizontal line. And if you were to plot y is equal to 5, right? Y is equal to 5 looks something like that. As x approaches infinity, right? It's always going to be the curve is always going to approach the constant value of 5, right? So the limit of a constant is always going to be a constant. So this guy right here is just going to be 5. And without graphing 2 over x squared, this is the part of limits where you have to think about it. One mistake that students tend to make is they plug in the value of infinity. Remember, infinity is not a number. So just think about it, right? 2 over a very large number, okay? I'm not plugging in infinity. I don't know, think of the largest number you can think of, 1 billion, right? And I'm squaring that large number, right? And this guy right here in the numerator is always going to be constant. Well, you were taught from day one in fractions, right? The lower the denominator is, or the higher the power of the denominator, it's going to make your number really, really small, right? When you have two people, if you have two pizzas and you divide it among two people, you would much rather divide among two people as opposed to 4 or 6 people, right? Because you get less of the pie, right? And so in math sense, right, 2 over, or constant over a very, very large number just goes to 0, okay? And you can experiment, right? 2 to 1 million to the second power, it's going to go to 0. So what you can do is just say, to show your work, don't plug in infinity, okay, because infinity is not a number. I know some math teachers will be very picky, myself included, if I teach calc next year. You're going to get 2 over 0, which is just 5 plus 0, which is just 5. Okay, and that's how you would show your work on a problem like this. All right, moving on. Let's take a look at part B here. Before I even do the algebra here with you, you can probably tell me what the answer is, right? Remember, we just stated that finding the limit at infinity of a rational function corresponds to finding the horizontal asymptote, right? And if you memorize all those rules, you would say, well, this degree is 1 less than this degree, right? In the numerator, then you would say, well, the answer, the horizontal asymptote is just y is equal to 0. And so when we, do this algebraically, the final answer should be 0. Okay, so this is the quick check. But I'm going to use that technique I showed you, which is dividing by the highest power in the denominator. If I take a look at my polynomial function here in the denominator, the highest power is x to the 4th. Okay, so that's what you want to divide every term by, x to the 4th. So let's do that. So it's just a lot of writing here. 3x cubed over x to the 4th plus 5x squared over x to the 4th plus x over x to the 4th minus 6 over x to the 4th. 2x to the 4th over x to the 4th plus 8x squared over x to the 4th and minus 1 over x to the 4th. Okay, so what I would do is cancel out common factors, and then you can evaluate as x approaches infinity. Okay, so the limit as x approaches infinity, this just becomes 3 over x 5 over x squared plus 1 over x cubed. Okay, so all your simplifying rational function skills, or rational expression skills. This one you can't simplify, right? These x to the fourths will cancel out. X squared over x to the fourth is just 1 over x squared, right? So it's 8 over x squared minus 1 over x to the fourth. All right, now this is the point where you can plug in a very, very large number, okay? And again, don't plug in infinity. Infinity is not a number, so don't plug it in. What you could do is start evaluating. You could say, well, 3 over a very, very large number, 3 over 1 million, that's going to go to 0. 5 over a very large number squared is definitely going to go to 0. And so forth, right? 1 over a large number cubed is definitely going to go to 0. A constant over a large number to the fourth also go to 0. Okay, so it looks like we have 0 in the numerator. We cannot have a 0 in the denominator, right? Otherwise, we have that indeterminate form. A constant, the limit of a constant is just the constant itself as x approaches infinity. 8 over a large number, that's 0. And 1 over a large number, that's just 0, okay? So after all that work, right, 0 over 2 is just 0, just as we predicted, right, because we did that comparison of the degrees way back in Math 3 when you're first introduced to rational functions, okay? And this is how I would expect you to show your work in the homework. All right, so let's take a look at this one right here. Again, before I even do a single algebraic step, right, you know the answer, right? In fact, this problem is actually the limit as x approaches minus infinity. Remember, it doesn't change. If you remember the beginning of the lesson, whether I go to positive infinity or negative infinity, it's always going to approach the horizontal asymptote. Okay, well, the final answer, right, because these degrees are the same, is just the ratio of these two numbers. It's 2 over 6, which is 1/3. But, you know, let's do this problem algebraically. So 2x squared over x squared minus 5 over x squared. 6x squared over x squared plus x over x squared. All right, so 2x squared over x squared, well, that's just going to be 2. Minus 5 over x squared. These x squares will cancel out. Plus 1 over x. Okay, now at this point, right, you can plug in a very, very large number. Okay, in fact, you don't even have to plug it in. Just think about it in your head. 2 minus 5 over a large number is just 2, right? You could just say 2 minus 5, 2 minus 0, which is just 2. And then 6 minus a very, very large number, right? 6 minus a large number, 1 over a large number is just 0. You're going to get 2 6, which is 1/3. And that is how you would show your work on a problem like this. All right, so far we've done some pretty basic ones, I would say. Like, you can pretty much compute this in your head, right? Before you even start, you can compute this one in your head. And the very first example where I had 5 plus 2 over x squared, you could probably have done that in your head as well. Now, what about this problem right here? The limit as x approaches infinity, where this degree exceeds this, right? And if you remember your graphing rational function days, right, you would have a slant asymptote. But, you know, we're asked to do this algebraically, and again, you probably don't have time to think about this graphically, you know, if you're under time constraints and you're taking the AP exam. So what I would do, again, use the limit property or the technique of dividing by the highest power in the denominator. The highest power is still x squared in this case. And let's see what happens when we do this. All right, x cubed over x squared, that is just x. This is still 1 over x squared. X squared over x squared is 1. And you have 4 over x squared. Okay, so if you were to plug in a very large number for this term, right, it's just going to go to 0. And in fact, you're going to have a large number plus 0, right? And then you're going to have 1 plus, 4 over a large number is just 0. So maybe, if you think about it here on the side, this is going to be a large number. This guy is going to keep going bigger, right? Because that's just x. And then this is just 0. And then 1 plus 4 over a large number, that's just 0. Okay, so really what you have is, right, this denominator just turns to 1. And if you were to simplify this, right, you just have a very, very large number. Now, think about it, right? This large number we don't know what that number is, right? Because x is approaching infinity. It could be a million, it could be a billion, it could be a trillion, right? And so do we say the final answer is infinity, or do we say it does not exist? And based on what your textbook is defining, because some textbooks say, okay, you could just say it's infinity, but based on the answers in your textbook, we're just going to stick with their definition. In order for the limit to exist, right, it actually has to approach a specific number. In this case, infinity is not a specific number. So we'll just say it does not exist. Okay, and you'll find that answer to be true in your textbook as well. Now, if you're just curious, like, what do you mean it does not exist? If you were to graph this, right, on, using Desmos, it would look something like this. Right, and if I say, hey, what's the limit as x approaches infinity of this function, right? This graph, if I go keep going this direction, x approaches positive infinity, this graph is just going to keep on shooting up forever, right? And we don't know what that forever is, and so you could just say it does not exist, right? And same thing if you say the limit as x approaches minus infinity of f of x, as we're going this direction, right? It's the curve, the y value is not going to approach a specific number. It's also going to be does not exist. Okay, so we'll just say does not exist, and this is how I showed the work for you.